and welcome to another episode of FooBar. In today's episode, we are continuing our chat with Ben Smith, developer advocate at AWS and one of the most experienced persons that knows about step functions. So basically, a lot of the things that you have been seeing out there about step functions, it came from his mind. So I'm so excited to have Ben today to talk about patterns. He has found out by experimenting and by working with step functions so long, so many interesting patterns that many organizations today use in a daily basis. So in this interview, we are going to deep dive on some of the most used patterns, in the most common patterns, in the most powerful patterns, in the newest patterns, and let's see what happens. So let's get to the interview. Hello, welcome back again, Ben. For those that notice, we are wearing exactly the same clothes and we're exactly the same position that the previous video with Ben. But magic of editing, you are watching this in a totally different week. Yeah. So here I am with Ben Smith. He did a really great introduction about himself and how he found step functions and why step functions are so cool in our first chat. So I will leave you the link in the description box. But now we are going to jump into another topic I wanted to chat with Ben, that are advanced patterns for step functions, because this guy here has crafted I don't know how many patterns. If he needs to write a book, because he's been naming all the patterns that he's coming up with. And every time I go and do a reinvent talk, says, well, this pattern named by my colleague Ben Smith. So yeah, you're here and you're going to tell us firsthand all the patterns that you have been building and naming. So
yeah, if I can, I like to name them as if they're like pop songs or something.
I think the names you have been given are kind of good because they're funny, but at least they're related to what the pattern is. So let's start with the first pattern. And I think this one was a little bit of a revelation for many people when I showed it the first time.
Oh, really?
Yeah,
yes.
well.
This one, like I think almost all of them, we were sort of discovered by building real stuff. And as a result of that, improving and iterating and then working out how to build that thing as a step functions workflow. So the first one is, it started off as a Lambda function, a big Lambda function. So sometimes called a Lambda lith, which I don't have a problem with, by the way. I'm not a purist. I think it's fine to have a big meaty Lambda function in many instances. But there can be problems with it, right? So let's talk about the problems with it first. So let's say we have this Lambda function here where I'm just kind of creating a REST CRUD API. I'm doing some actions with the DynamoDB table. Maybe I'm creating records, I'm updating, I'm deleting records, and I'm doing that using a Lambda function. And because I've been building with Lambda, I learned that API gateway is a nice way to front that Lambda function with the URL. So I put API gateway in front of my Lambda function, and then I can authenticate and authorize calls to Lambda. And then my Lambda function can perform stuff in DynamoDB and return the results. So that's fine, but the challenges that I have is there's a few things, right? The first, and this is very common that we see customers doing all the time, they go down this path. So they get comfortable with the sort of DynamoDB from Lambda and API gateway in front of Lambda. They end up routing everything to their Lambda function and then adding logic in their Lambda function to handle that routing. So, based on the request, do I create, update, or delete? And I'll write that in my code with some sort of switch or case
post,
statement.
if put, if delete, and you're so couple.
Exactly. But this is what people get into because they've got to build quickly, right? They've got to keep up with the pace. So they've got something that works, they go into it, they just add to it. And so the first problem is I'm adding code now that's routing within my Lambda function. The next is that now I have a Lambda function that's doing lots of different things, sometimes with lots of different services as well. And it needs permissions to be able to do all of those things, right? So my function becomes fairly loosely permissed, and it's getting, more and more access to my account the more things I add to it. So that's not great either. And then there's other things like the configuration of my timeout and my memory config. These are things that affect my workload. They can affect the cost of my workload. So all of this is the same regardless of which one of these actions needs to be performed. So what many people will tell you to do is this, and this is a good step, I think, which is to break this Lambda function out into discrete Lambda functions that are for one specific purpose. So I have one to create, one to update, and one to delete. Why would I do this? So what it means is that I can move that routing logic into API gateway configuration. So API gateway now is handling which one of these functions to call. So I've reduced a bunch of code there. That's good. It also means that I can apply the permissions for each one of these functions more accurately. So my create function is only allowed to create items on DynamoDB. That's all she knows how to do. That's the only purpose in life for this Lambda function, right? And the same with each function. All they know how to do is what they've been configured to do, and that's their limit, that's their boundary. And the same with the timeout, and the same with the memory config. It can be more accurate, it can be more cost effective like that. The problem that you'll find is your application grows like this. This is just 3 Lambda functions. So here I've got, each function's got 20 lines of code, more or less, that are doing really similar things with slight differences. And as this grows and expands, it becomes quite difficult to manage, to track, to inspect when something goes wrong. And this becomes a problem for people sometimes.
And then if one day you want to change something in the way that you work with Dynamo or like things like that, you need to go to all these 60 Lambda functions.
Yes, yeah,
and
you need
change
to
it
drill down.
everywhere. Fun stuff.
Yeah, so that's where this pattern comes to the rescue. So it's the REST CRUD API using step functions. So what I have here is I have my API gateway URL in front of my workflow, and I proxy everything that's valid onto my workflow. And then I have a single state in my workflow that does the routing for me. So this is deciding whether I get, put, post, patch, whatever. And then I do that action directly from step function. So I use the step functions SDK or an integrated task state to perform that action directly, and then I'm out, right? There's no cold start time. There's no code to manage. There's no invocation costs of Lambda.
That cold start is an interesting thing, because I have many customers that say that they like to build a little Lambda list for these things, because things like delete or update maybe had really little hits. And they are always cold. So if they put them in the same package as get, then it will be always warm and it will have a faster response time. But with this solution, that's not a problem anymore.
Yeah, that's a pretty smart solution, really, I suppose, in some respects. But you're kind of coding around a problem there, aren't you? But I think this is probably more effective way of doing the same workload. And the reason we came up with that is because when we were building this application called Serverless Espresso, which is an application that the DA team, the developer advocate team, built for reInvent of 2 years ago, for a demonstration in the expo hall at reInvent in Vegas to let you order a cup of coffee from your mobile phone. So we wanted a demo that people could use without even really knowing they were using a serverless app. And so we ran this demo at reInvent, and we had one of the microservices was this REST CRUD API called the Order Manager Service. And it was like the first version I showed you that uses API Gateway to Lambda to various other services, mostly DynamoDB. And we had some problems during that week. We had some latency issues. We had some problems with things running in production that were very difficult to debug in this sort of stressful, busy week, right? And we sort of got through reInvent. It went fine. But the first thing we did the next week was we went back and we reevaluated this service, and we completely rebuilt it as a step functions workflow, which is essentially that REST CRUD API as a workflow. And the thing I would draw attention to here is that there's only one Lambda function now, because we found out all we really needed Lambda for in terms of compute was this one thing, which was to sanitize the order, to check that the order coming in was a valid thing in that particular time box window. And we did need to run some code for that. But everything else, we didn't need to. And this workflow runs as an express workflow, which if you go back to our previous talk, you'll understand is it was a cost-effective way of doing this, because it only took couple of seconds to run, and because we needed it to be synchronous so we could return the response straight back to API gateway.
And at least one thing I learned from my reInvent talk when I was doing these low latency applications is that step functions performs very equally. It doesn't matter if you have one request or if you have like 100,000 requests. It's very stable, the response. So there is no call times, there is no peaks, everything. So for this type of backends, like interactive workloads, it's very good because you can basically always expect the same latency, no matter what kind of hit you do to your backend.
Yeah, and if you can run that as an express workflow with this synchronous mode, then it's a great alternative, right?
Yes, so that's the first pattern you want to show us. And what about like other kind of patterns, like maybe something to catch errors? Because we talk a lot about, I don't know, what happens if something goes wrong, and Step Functions has a lot built in for error management.
Yeah, it's I like to start sometimes by like showing this quote from Werner Vogel, the CTO of Amazon. So he's well known as having been quoted to say that everything fails all the time, right?
Famous quote.
Yeah, it's a good one too, and it's a good one to be thinking of as you're building as a developer, I think, because why wouldn't you build with that in mind, right? Make your applications more robust because of it.
Exactly, and the more we integrate and make these distributed applications, the harder is to know like where it will fail, and more if we are integrating to systems that we don't control.
Yeah, well, with step functions, it has this built-in mechanism for managing and handling failures, right?
Yeah.
It's part of the orchestration piece. So there's a couple of patterns which play really nicely into this. And the first, I think they're both very well known, really. The first is the Saga pattern. So here is what it enables you to do is to roll back a sequence of events in a particular order, right? So a nice example, I think, is like a holiday booking system where the happy path, I might book a hotel, book a flight, book a car, and that's fine. When we finish there. If at any point I need to cancel or I have a failure on each one of these things, then I can capture that failure and roll it back. So in the case of booking a hotel, I can catch that, roll it back. If my book a hotel passes, but my book a flight fails, then I need to roll back in a particular order. And it's a nice visual way you can see I kind of waterfall down from each state.
Yeah, that's what I love from these step functions, because when you are building the Saga pattern in code, sometimes you need to really test a lot to make sure that you are always reaching the right state in the right time. But when you have this visual interface, it's so clear to know what happens after what, because it's the drawing, it's just the arrows and everything is pointing to the right place. So it's so much easy to understand that if you have built the workflow correctly. And sometimes these Saga patterns can be very complicated, because when you are doing the Saga, basically you need to revert every action that had a side effect. So it can be quite complex.
Yeah, the visual aspect like reduces that mental load for you, doesn't it?
Exactly. Yeah. So this is a great pattern, and it's very simple to implement in step functions, because you just catch and voila.
So that's the first one. Yeah. The next one is often spoken about in the context of event-driven applications, I've noticed recently, and that's the circuit breaker. So the idea here is that you will prevent calling some downstream service if you know that your circuit or your application is broken or unhealthy, right?
You need to change this slide now, because we have the HTTP invocations from the step functions, and I think that's a great example for circuit breaker, when you are calling a third-party service and you don't want to overwhelm them with kind of calls and
really good example. Perhaps you're calling something that can't scale quite as well as your workflow can, right? Something on-prem or in another area. Yeah,
exactly.
So what you do here is you have something that maintains the state of your circuit or the state of your application. So in this example, it's a DynamoDB table, right? So the first thing your workflow does is it checks with that DynamoDB table, gets the status back, and then it uses a choice state to say, is my circuit closed? Is my application good? And if it is, then it can go ahead and make that HTTP call or whatever it is. In this case, it's a Lambda function just for example purposes. And then it exits. And then the next request comes straight in and it does the same thing and it makes that call. But we catch the error, right? So if there's an error on that downstream service, we catch that. We update the circuit to say, okay, there's a problem. We're going to open the circuit. And then the next request that comes in will actually take a different path, maybe some escalation path, because it knows that our circuit is open and we should not go ahead and call that downstream service.
Yes, that's a very good pattern and a classical one. That with step functions, it's simpler because if you wanted to do that with Lambda, sure, you can do it, but it's adding a lot of extra calls before calling maybe that HTTP endpoint that you want to call. Now you can take it out and just have either the Lambda function or the call to the HTTP endpoint directly, and boom, you're ready. So
yeah, it's all about stringing together the services for the thing that they're best at, right? And then using step functions to orchestrate between them.
I want to stay with that line because I think the next pattern that I have in mind, it's really about picking the right service for the right task. You have one that you have been using in Serverless video that I find fantastic, to is picking the right compute, because we talk a lot about like when to use Lambda, when to use containers, and how to decide. And
yeah, so I'm not going to pretend I understand exactly when to use Lambda or containers for like any workload.
But if you know, you can build it into a step function.
Exactly. We found the sweet spot for this particular application, and we use step functions not only to find the sweet spot, but to work with it, right? So what we had in this application serverless video, which is another demo we built for reInvent, where we allowed people to live stream video from their cell phone. And when that live stream finishes, what we wanted to do was process the live stream files, these TS files of about 8 seconds, put them together into a single MP4 file that we could do some further data processing on. And so in order to turn it into an MP4 file, we first of all use Lambda and FFmpeg, which is this nice library for working with media files. And it worked pretty well, actually, until we started doing longer streams of 20, 30, 40 minutes. We started to hit the Lambda timeout, which is 15 minutes, right? Lambda was needing more than 15 minutes to convert these TS files into an MP4.
Yeah, because it's very tight, the length of the MP4 to the amount of time the Lambda runs for. So that there are many, and I think that's one of the use cases. Lambda or containers, like you need more than 15 minutes.
Yes, yeah, exactly. This is a good one to start with, I think. So the first thing we did was we would catch that error, because we didn't necessarily know when it would time out. It wasn't always clear to us because of all the different tests we were doing. So we would catch the error and we would say, okay, if Lambda times out, then we'll try Lambda first, and if that times out, we'll run this in an ECS Fargate task instead, and we'll use step functions to spin up that task, execute the code, and we'll get the same response as what the Lambda function would have given us, right? And so this meant we got around this timeout limit, and we were pretty happy with this for a while. But the more testing we did, the more we found there's a sweet spot, which was if we had a video stream of about 20 minutes or more, that's when Lambda started to time out. And look, there's probably some optimizations we could have done with our Lambda code. I'm sure we could have, pushed that limit up, but time was a constraint as well with this. So we thought, what's the best way to work with what we already have and the time we have? And we decided we can preemptively check the duration of our video because we have that on the metadata of the event that starts this workflow. So we decided to say, if our video is longer than 20 minutes, we'll process it in an ECS Fargate task. And if it's less, then we'll process it with Lambda. And so most videos were less. I would say like 80% were less, but the odd one was longer, and we were still able to, get through that and process that into an MP4 just by using step functions to decide which one of these compute substrates to run.
Yeah, and the cool thing here is nothing to do with the functions, but you can use exactly the same code in containers and in
Yeah,
Lambda almost, because you can run a
almost.
container.
Yeah, the only difference we have is that we needed the exports handler in Lambda, and we don't have that in ECS. I think, though, you probably could have exactly the same code if we were able to figure out how to like simulate the exports handler in ECS. Maybe it would be possible to have exactly, but it was pretty close. This was just one line that was different.
Exactly, but that's very cool because then you can apply this pattern, pick the right compute for your job,
Yeah.
and write exactly the same code. It's just a little integration layer there, but maybe your real code is in a module somewhere else, and you just import that, and boom.
It's a really
So
interesting one, isn't it? I think there's a lot of potential for
there
this.
is.
I think we'll try it with all sorts of other things going into next year, actually, going into 2024 and beyond.
But this is the examples that I was saying at the beginning. So many patterns that you have been building through these years of working with step functions, because all these things just came from you building things and then showing to the world like what kind of things you can do. So it's really,
the
really
best way,
cool.
right?
Yeah. Should we jump into a little bit more complex scenarios? Because step functions are really cool, but what happens when we have a lot of things running in parallel? And I think that's one of the powers of step functions. We launched a distributed map that allows to run 10,000 things at the same time. And I know you have like a lot of patterns built around that.
Yeah, so I think I mentioned the video we did previously that there's two patterns that I always like to build with. The first is the emit and wait pattern that we spoke about before, but the other is this fan out pattern that you can get with step functions, and it's all about breaking down your task into smaller tasks that you can then run in parallel. I think that's like the fundamental thing of cloud and serverless compute in general, is how can I break down something, use the resources available to me that AWS brings, and run those things in parallel, right?
So you can finish faster.
Yes, and that's a great use case for step functions. But there's different ways to think about parallelism with step functions. The first is simply just executing a workflow multiple times at the same time, right? So lots of parallel invocations of the same workflow. It looks a bit like this. If any one of those fails, it shouldn't affect the others, because they're executing without knowledge of each other, if you like, right? Then you have something called the parallel state. So this is a type of state within step functions where you can run a fixed number of branches in parallel, and each branch gets the same input, and it runs, and then it produces an output, which is when they've all finished, then the parallel state exits, and the result of the parallel state is an array of all of those outputs that gets handed to the next.
And here it's very useful when you have to apply a lot of different methods or whatever that are kind of independent from each other. So for example, if you are doing validations, you can validate the address, you can validate the social security number, you can validate, I don't know, the education, and you can run all these different validations maybe against different systems, and then boom.
Yeah, you don't need to do those things in parallel quite often, right?
Well, you can do them in parallel. The thing is that
yes, you don't need to do them in series as well.
Exactly.
Yeah, exactly. Just as an aside, though, this concept of the parallel state led me on to a nice little tip that I want to show you, which is when you're doing things in series, I'll get it right this time, and you want to pass a variable from somewhere high up in your workflow to somewhere lower down, typically what you'll do is you'll like pass it through the parameters like this, and you'll have to keep checking that it's there, and probably you got that wrong, you've typed that wrong at some point.
How many times
will fail. Right.
You lose the state, or then you carry a massive amount of state because you don't know how to just grab that little piece.
Push the whole thing through, right? Exactly. Yeah, everyone's doing the same thing. So this is a good tip. You'll like this. This is a pattern called the data preserver. And so here you use that parallel state to say, I'm going to have one branch to do all the work, and the other branch is just going to hold all the data that I need for later on at the end of my parallel state. So in this example, my workflow is started by an event that includes a task token. And when my workflow finishes, I need to send that task token back. So I store my task token in this other branch. And then when it's all finished, my task token's ready for me to return back, right?
That's awesome. So you save a lot of state moving around.
Yeah, it's neat, isn't it?
I'm taking a note on this one because I keep on handling state in the most weird ways in step functions. So
cool. I wanted to show you that because I think that's like a handy trick.
yes, I'm excited about that one.
Okay, so I'm going to skip some of the stuff about error catching in parallel state because I want to talk about dynamic parallelism. So this is, in step functions, it's called the map state. And what this allows you to do is to hand an array of items to a series of substeps. And then those substeps, which are the states inside your map state, will run concurrently, right, against each item in that array. So you could say you want to run against each item all at the same time, or you could even make it single-threaded and say you want to do it one at a time. But what this allows you to do is to have this fan out.
Typical map function in most of programming languages, that you pass to an array a map, and then the function that you want to apply, in this case, is whatever is inside that branch, and boom, everything runs in parallel.
Yeah. The first time I used this was when we built that website Serverless Land, which is a great resource for anyone that wants to learn more about anything to do with serverless, including step functions. And we used the step functions workflow to populate the very first versions of Serverless Land, which originally was just about aggregating blog posts into one place. And so this is what that workflow looks like. It still runs every single day, actually, to populate Serverless Land. And what it is a workflow where we first... Oh, this would be replaced now with the HTTP state, wouldn't it? We could update this. Yeah, originally we were using Lambda to make a request out to an RSS feed to get all the new blog posts from that day. That produces an array of blog posts that we then pass into our map state. And then for each item in that array at the same time, we scrape the metadata of that URL. So we get an object that represents that blog post. And then we save that object to GitHub, which is where we have our static website. And then when that's finished, we rebuild the site and we push that back out via Amplify. So what this let us do was to, scrape these URLs of new blog posts and update maybe 10, 20 all at the same time, and then rebuild the site dynamically.
This is very, very powerful.
Yeah. So we actually improved it later on. And if you go back and look at the first video that you and I did before, we were talking about cost optimizations and standard workflows, how they're built based on state transitions. So that's why we did this next thing, which is the scatter, gather, or the fan out, fan in. So here we still get an RSS, via an RSS feed, we get an array of blog URLs. We scrape the metadata from each blog URL, and that produces an array of metadata with different objects. And we move the save to GitHub array outside of our map state. So that means we're only calling this once and not for every individual item, right? So we're saving cost. We're using this fan out and fan in method.
And that's the cool thing of this map state, that it will centralize the results altogether. And that's sometimes quite one painful thing of running the same function, for example, in parallel, is that how I can handle that end state, end result into one place. If you can have multiple functions running in parallel without step functions, append to an S3 file and then manage it manually. But this does it for you, and it keeps the state. If something fails, it just has everything built in. So it's way easier than.
Yeah, really good point, actually. Yeah, I should add that in to the next time I do a talk on this, is that you have all of that data gathered back for you without having to go and...
Because that's a very painful part.
Yeah. And
now you're doing here 40, but I think you're next going to the 10,000.
Yeah, exactly. So that map state, which still exists, it's now called what's it called now?
I think it's the map state.
Just called map state.
And the other one is the distributed
It's called the inline map state, I think it is.
Okay.
Yeah, so that allows you to get a concurrency of about 40 items. And what customers were doing, they were embedding those map states within more map states, within more map states. It's quite clever, but awkward, right? So last year at reInvent, we launched something called the distributed map state, which gives you a max parallel executions of 10,000. So we've gone from 40 to 10,000.
Little scaling.
Unbelievable, isn't it, really? And there's some cool things with this as well. So the first is that you can point it at your S3 bucket, and you can say, for every object in this S3 bucket, I want to run these steps in parallel. Or you can point it at an object in your S3 bucket, like a CSV file or a JSON object, and you can say, for every item in this file, I want to run my parallel map state.
That's important because step functions can handle a payload of 256 kilobytes. I'm very bad with letters. And if you have a massive amount of things that you want to process, S3 will help you, because then it'll like just point to the S3 file with all the information, and the functions will take it from there one at a time, 10,000 times.
Yeah, exactly. You're not having to use a get objects state and then pass that in, and it's all managed for you. This is a nice pattern to show off that scalability, I think. And this is the other pattern that I'm always using, right? And this example is for something quite trivial. It's a GIF generator to show something like a timeline scrubbing application for a video, right? So what this does is it generates a GIF animation for every 30 seconds of an MP4 file. And it works like this, right? When you drop an MP4 file into a bucket, it starts the workflow, and it tells you the location of that MP4 file. It then uses a Lambda function with ffmpeg again to say, okay, if I'm going to make a GIF animation for every 30 seconds, let's produce an array of metadata objects to say where each GIF needs to start and end. Where does each one of those files need to exist? So we're not doing the work, we're just figuring out what we need in order to do the work. We save that object in S3, and then we pass that into our distributed map state. And this is the magic bit, right? Now there's an individual Lambda function invocation for each GIF animation in parallel.
And those are very small because they are just working on that tiny bit.
Yeah. So it doesn't seem interesting for a little silly video of me waving in my office, but if you scale this out and imagine that if my MP4 file, whether it's 10 seconds or 10 hours, it's going to take about the same amount of time to run this workload, because you get an individual Lambda invocation for each GIF animation in parallel. So it's back to that concept of breaking down the task into smaller and smaller workloads that you can run in parallel using the resources of cloud compute, essentially.
Yeah, and this is I think also being able to export the results without you having to do anything into one place, getting everything together. It's super powerful. So because how to handle 10,000 invocations and the results of those, it's just painful. So so this is a great pattern.
So this pattern, it comes with some interesting kind of cheeky bonuses as well, right? So when you run your distributed map state, the steps within your distributed map state are actually running as their own separate workflow execution. And so that means it has its own execution history, its own payload limits. It's not really part of your workflow in the way that it runs. And the first time I realized why this was useful was earlier on this year, building an application where, first of all, this application, it used to scan GitHub for all the repositories that we were interested in the DA team, and it would use the GitHub's API to save all the interesting data about all of those repositories every single day. So we could store that for later in the year. And then about 3 months later, I built a workflow to do some analytics of that data, right? So the first thing this workflow had to do was to grab all of the entries from this DynamoDB table that had ever run about all the GitHub repositories for the last 3 months. So I just used the scan query, and straight away we hit that payload limit that you were speaking about earlier, that 256 limit, because I'm trying to pull down nearly 3,000 very large items. And straight away I couldn't run them in parallel because of that payload limit, right?
So
talking about breaking down into smaller and smaller chunks that you can run in parallel, that's where the distributed map state came to the rescue. So I did a different scan to just get the individual repos that I want. And then I put in parallel each one of those individual repos into a new scan of a child workflow to get the number of entries for each repo. So instead of 3,000 entries, I've got 90 items this time.
And this is also a better pattern from the perspective of Dynamo, because when you do a scan, yes, Dynamo maybe has a bigger payload for you to return you in the scan, but you will reach that payload limit as well there.
Sure.
So now it's kind of, you have the parent, and then inside the parent, you have the children. And I can even tell you, you can even optimize this database.
I bet. Yeah.
With primary and sort keys, but well, that's a different talk.
Yeah. Why not? Let's go. Let's keep going.
Well, this is really good.
I think what this shows is, it's back to that. There's two things, right? It's breaking down things into smaller tasks that you can run in parallel, and it's understanding the features and functions of the service to get around different, rough edges that you might not have expected. So, I was able to run this workload very quickly just by having a rethink about how to do it.
Yeah, and I think a great takeaway from these patterns and our chat today is that for the audience watching, it's like all these patterns came from you building. And if you look at how you've been telling the stories, it's the evolution on how you've been learning and how you've been refactoring and have been getting to this optimized solution. So that's something that many of us are like afraid of building it wrong the first time, but that's the way to build, and that's the way to learn. So build it, test it, make sure that you learn where are your sweet spots and where are your problems, and then refactor it and keep on learning, because I think that's a great example of what you have been doing here when making these patterns and finding these really optimized solutions for these problems.
Yeah, absolutely. And that's one of the benefits of serverless, right? Is you can get things out the door very quickly and then iterate on it.
Exactly. And if nobody's using them, they don't cost you anything. That's always nice for developers when we are breaking things.
Yeah, exactly.
You don't need to put all these big expensive things up just in case. But I think this was amazing, and it's great to see all these patterns, and also the chat we did on cost earlier on. If you have not watched that one, you should, because I learned one new pattern today and I will apply it.
Cool. Which one was that?
Well, the one of how to preserve the data, because I keep on messing that down. I'm waiting for variables to be one day out. I don't know, step function, please listen to me.
Yeah. That would be good. Global variables would be good.
Exactly. But while they are not out, I think I will embrace that parallel pattern with the data preserver.
Do it.
Yes. So thank you very much, Ben. It's always a pleasure to chat with you and to learn stuff about step functions from you.
My pleasure.
Yes. And where people can find you, I will leave you all the social in the description box, because you're very active, at least on social media, and always putting the new patterns that you discover through the years. So it's always worth the follow.
Probably, LinkedIn and Twitter are the two that I use the most, I suppose. Yeah.
Cool. So I'm pretty sure people will reach out there. And thank you very much. Have a lovely day, and I see you in another episode.
Cheers, Marcia. Bye.
This was the video for me today. I hope you like it. Chatting with Ben is always awesome. You can find the first part of our interview in this card here. I leave you the link there, so if you have not watched that one, go and check it out. We talk about cost analysis, and you can also find this playlist where all the videos about step functions have been posted. So I have been making quite a lot of videos lately about step functions, so you should go and check that out as well, so you learn everything that there is out to know about step function. And with that, I see you in another episode of FooBar. Ciao, ciao!